Okay, question number one here. It says a 10 kilogram mass is being pushed or pulled by a string across the table at a constant speed of 2 meters per second. The key here is constant speed. Constant speed tells me that all the forces are balanced. The tension in the string is 80 newtons. Draw an interaction diagram and a free body diagram for the mass. So for A, interaction diagram is just saying, well, we've got this mass, so we've got the mass here. And then we've got all the forces that are connected to that. So we say that there's gravity here. Actually, I'll make these gravity. It's on a surface, so we know there's a normal force. And we know that there's a tension. And we know that there's friction. So now for the free body diagram, I just know that my tension and my force of friction cancel out. And I know that my normal force is canceled out by the force of gravity. And this one should be a little bit shorter here. Find the numerical values for part B here. So for B, I'm going to write an equation. Even though I know I can do this in my head, I want to know what all the values are. So the sum of the forces on the y-axis I know are 0. And I know the sum of the forces on the x-axis are also 0. So I'm going to fill in variables here to just sort of confirm that. So for the y-axis, I know that the force of gravity, mg, is equal to 10 kilograms, and then multiplied by, and I'll use negative 10 to simplify this. So I know that the force of gravity on this is 100 newtons, and that's negative. So in order to solve for the normal force, we want to be careful with that and not just assume that it's 100, so we want to confirm that with an equation. So what I'll do is I'll set an equation to 0 and say the forces on the y-axis are equal to mg plus the normal force. And so I know that mg is negative 100 plus, and you just be careful, I'll write force normal so we don't mix that up with n. And that equals 0. So if I add to both sides 100, I know that F sub n is going to be 100 newtons. For the x-axis, I also know that the sum of the forces on the x-axis is 0, and that makes up the force of tension plus the force of friction. Now, if this was accelerating, some people ask me about, well, what number goes first? I usually make it a habit of putting whatever one wins as the one that's going to be first in the equation. But since it's a constant velocity, it's sort of irrelevant. So we end up with 0 newtons equals, and then we know we're pulling 80 newtons plus the force of friction. So for this one here, I know it's going to be negative 80. I'm going to subtract 80 from both sides. And so the force of friction is equal to negative 80 newtons. And in the question, they didn't verify like which way it's going. It didn't say right or left, so we just assumed that it's going to the right. We could have done the entire problem to the left, and all of it would have done is change this to a positive number. For C, I'm not going to do this quantitatively, but if we sketch this out for velocity versus time graph, v versus t would be a straight line, and you'd have 3 meters per second somewhere over here. And then for the position versus time graph, you would have something like this here. Now, it didn't say that it was moving from rest, so it could be anything. It could be this, but it's definitely got to be linear. For the next problem, it says a 5 kilogram sled is being pulled by a rope at, again, a constant speed on a level surface, and that's super important that you understand that it's level. The force of friction between the sled and the snow is 10 newtons. This is almost identical to what we do in the lab. So the force interaction diagram, I'm not going to do that. It's just the same. It's just you're basically just putting sled here, and you're connecting like a mind map for all the different forces that are involved. I'm going to go right to the free body diagram. And the free body diagram, again, it's a sled, and it's on some sort of snowy surface, so it's going to have a normal force here. It's going to be a force of gravity here, or you can say mg. And then we know that there's a force applied here, and that force is unknown, but we know the force of friction is here, and that force of friction is 10 newtons. In all actuality here, these should be a lot longer because it is 50 newtons, so it should be 5 times longer than the force of friction. I can't fit it, so I'm just going to do a little bit bigger. but as long as they're equal, that'd be good enough. So find the numerical values on the sled. So again, we can set up equations here knowing that the sum of the forces on the x is equal to the force applied plus the force of friction. And I know that this is actually a negative number, and I know that this is 0, so I know my force applied is basically like saying x plus negative 10, and so I know my answer is going to be positive 10 newtons for the force applied. For the y-axis, I know these two cancel out because you're pulling the string, and it doesn't say the rope is horizontal, but it didn't give you an angle, so you assume that it is. So for the force on the y-axis, the sum of the forces on the y-axis, we know that's also 0, and that's also F sub g plus the normal force. And so again, if we sub in the values here, the sled is 5 kilograms, so we know that's negative 50 plus normal force equals 0, so the force normal is going to be 50. And I've bounced back and forth between using n and F sub n. I shouldn't do that in the same problem, but you know what it's supposed to be. Person pulling the rope stops, and then all attentional force goes out of the rope. Draw a new free body diagram. So all that would mean is that we've got this force of friction here. It doesn't change the normal force. It doesn't change the force of gravity. And what will happen here is the sled is still moving in this direction here, we assume, so it's going to eventually slow down and stop. And then it says here, what is the displacement of the cart from the time 0 to time 2 seconds? So for this, here's my graph here, we would just figure out the area of this. So we know from the problem that the velocity is 4 meters per second. It doesn't say that in the problem, but if we use F equals ma, we can figure that out. So I end up with an area of base times height, which for this is going to be 4 times 2 is 8. Now it says find the displacement for the entire time that the sled is moving. I would just add to that this piece right here, which would be 1/2 base times height, which would be 2, change in my base of 2, multiplied by a height of 4, divided by 2, which would give us 4 meters. So the total distance it travels would be 12. So this situation is it's a modified outward. This one you need to be careful because a lot of folks forget to do free body diagrams for both objects. So for this one here, it says a 5 kilogram block is moving at a constant velocity of 3 meters per second, and it moves across the table by a 2 kilogram mass that's hanging. So now what you need to understand is that if this block has a velocity of 3, so does this block. If this block accelerates and this block accelerates, and they accelerate at the same rate. In this case, it's a constant velocity, so we know that there's got to be a force on this one that's pushing in the opposite direction. So for this, to draw a free body diagram for the 2 kilogram mass, it looks like this here. We've got our mass here. Actually, I'll just draw a dot. We know that this is 2 newtons down, which is mg. So we know that this right up here must be the tensional force, and then we don't know what that value is until we do an equation for that. Draw a free body diagram for the 5 kilogram mass and find the numerical values for each of the forces on it. So for this one here, I'm going to run out of time with this video, but this one here is the larger of the two masses. It's 50 newtons. Sorry, 5 kilogram box, 50 newtons. I made a mistake here. This is 20. And so then it must be a normal force of also 50 newtons up. Now, there's a tensional force here, T, which is unknown, and there's a force of friction, which we know is going to be the same value. Now, when I take each one of these and I look at what the forces are that we don't know, which is tension, we do know that this tension right here will actually be the same tension as this. So for this, I would pick the first mass, which is actually 20, not 2. It's negative 20 down. So again, if I do my equations for this, which we can do some of these in our head, although on the exam you don't want to do it in your head. But we know this is negative 20 plus the normal force. So we know that it's going to be 20 newtons is equal to the normal. Now, I'm sorry, not normal, the tension. So the tension in that cable is the same for both masses. That's not always the case in every situation where you've got a hanging mass like that, especially if this was on an incline. So what we're going to do is we're going to take this tension and make this tension also 20 newtons. And that also tells us that the force friction is 20 newtons, but it's in the opposite direction. And the last portion here is find the displacement of the 2 kilogram mass after 3 seconds. Use any method you can, but you must show your work. So I would use this here. It would just be anytime you have constant velocity, it's going to be v times t is equal to delta x. So it would be 3 meters per second, which is the constant velocity, multiplied by 3 seconds, which is going to give us 9 meters. Now you could have done a graph for this as well. You could have graphed this and said, well, it's going down. At least we're talking about a 2 kilogram mass, so we have to make sure it's a negative number. And then we'd figure out the area. If we said, well, it moves at 3 meters per second for a time of 3 seconds, we know the area of that on a velocity time graph would also be the displacement.